Sorry, I was just disconnected. The network just disconnected me. Sorry for that. I think people can hear me now. If you can hear, somebody should indicate that you can hear. Okay. Hello, can somebody hear?
Yes, sir.
Okay, yeah, sorry. I was disconnected by network and just a few minutes and I have to start. Let me just start from the beginning because that was just a small clip. So we are starting with a relationship between probability and statistics. And statistical thinking starts with probability and ends with probability. This is my own maxim. And another person said the world we live is in unpredictable. The world we live in is unpredictable. We want to understand it without going into detail of law of physics and advanced field of science. Probability and statistics is the only possible way. So another person, John Fowler, said, statistics is a well-defined subset of probability theory. Probability theory covers every aspect of the mathematical description of randomness. A statistic is a function of a random variable defined on the same space of that random variable. People often say statistics when they mean data, which is one reason other people find this subject confusing. But a very important field within general probability theory is sample statistics. So this person, statistics is a subset of probability. And what he called sample statistic here is what we call descriptive statistics. When you take sample, that is, you take sample and you describe the sample. So what is in the population, trying to draw inference from the sample to the population is inferential statistic. So that person now will be population statistic. Now, there was an allegory given by Plato. Plato compares our human condition to being tied up in a cave, facing the cave wall. As you see some people sitting in a cave here, and they're facing the wall. That's what Plato equates human condition with. Behind us is a fire. Outside there is a wall full of fascinating objects, and sometimes puppeteers come into the cave to animate objects. Look at the puppeteers here, in between the fire and the people. Except we can see them. As they stroll behind us, they agitate the object in front of the fire, and all we see are the shadow projected onto the wall. So what Plato was saying was that idea, most of concept we want to understand, they exist in form of idea, in the world of idea. Until somebody bring it to reality, it is remain idea. So you see that until maybe you just take sample, what you are seeing is just shadow. Because just like what we know, what exists in the population, there's no way we can study the whole population in many instances. So we take sample. We take sample to we now do descriptive statistics and try to make an inference. And what we are seeing is this the shadow, it's not the real thing. It's the shadow that we just look at the shadow. The reality may be too big for us to study. And that is what, and that is why at best, the best we human can give is that, this is the latest development. Then what is latest development in 30 years old, in 30 years time, become obsolete. What was raining in 20 years ago is obsolete now. So, and it's the same thing. Even the latest evidence we will provide tomorrow, next tomorrow will become obsolete. Now, let's move further. So as a way of introduction, I want to quickly look at the relationship between statistics and probability. Statistics are used to quantify observation of phenomena whose behavior is predicted by probability. So probability is the predictor. Whatever you predict, statistic is what explain it. You know, it's quantify the observation. For example, you want to know what is happening in the population, what proportion are diabetic, what proportion is there of the population is diabetic. So it's, the issue is a matter of probability, you are not even sure. You just create a probability model. You now take from that, you don't know that the sample size is a probability model. So after putting some things, okay, you say this should be the adequate sample size. The power is high enough. So you now take sample. So it is a statistic that will now, when you carry out your observation, is a statistic that will now explain it. That is descriptive statistics. And inferential statistics also that will now try to make inference about the real, what is the population. So what you are actually seeing is a shadow of the real thing predicted by the probability. So probability is the predictor, statistic is the quantifier of the observation. What was predicted by probability. So the mathematical language, probability is the mathematical language of randomness, which enable one to reason about or make predictive statement about outcome of physical system or processes that have randomness or uncertainty. We're going to explain that. I think there's a place we talk about randomness. When you say randomness, is anything that any variable that the result is as the outcomes as a result of random process. So I don't want to sound too mathematical. For example, if I want to know the height of people, or okay, let's say the height, or let me even say simple thing, the sex of people in this class. It's just for me to look at ask everybody, put on your camera, I want to know your video, put on your video. I can see, I will take the data, I will count. I know how we are 20 and 12 are female and 8 are male. What I've just done is a random process, And the result, what I got from it. So the sex now is a random variable because the sex is not fixed in the sense that all of us don't have the same sex. But if maybe it's men conference or women conference, that all of them are women, both the speaker and everybody is a woman. Sex is not a variable, it's not a random, because you already know that how many of us, how many of you there, you are 200 women. You don't even need to know how many sex. So sex is not a variable. But if the participants are both men and women, you just have to carry out the process of identifying, counting how many are men, how many are women, identify the sex of the participant. That process is a random process. So it will give you different results. So now sex is a variable because the outcome is a process of a random, is a sort of random process. And that's the way mathematics they express their own statement. Okay, statistics describe and summarize characteristics of observed outcome or data, extract pattern from it, and make statement about underlying mechanism or intrinsic structure of the physical process, system or process. So can you see probability try to predict? So if you study this population now, what would be the prevalence of diabetic among them? What would be the factors that are responsible for diabetes? Prediction. They try to predict. So, and it's based on everything you do about the appropriate sample size and many things you want to do. They are just prediction. You cannot be 100% sure. And when you get the result also to even extrapolate, is it the same thing with the population? Is true, is still probability. So probability is more theoretical We have practical aspect, it's more theoretical, while the statistic is more of the practical aspect. So the probability does the prediction. So we now ask the probability, we now ask, okay, take certain number from the population and examine. The examination is being carried out by statistics. And through probability also, you now project what it will be, because you are not still certain, because it was still based on probability theory, because you took sample, not the whole population. I think the next slide will explain better. They are more like infographic. So probability deal with prediction of the future event. Then statistics is used to analyze the frequency of past events. So if you look at it, when you are do your sampling size, and you do your sampling, you are envisaging what will happen. By the time you are taking the sample, you describe it with probability, with statistics. Statistics is telling you the sample you have taken, this is the result. So statistics is telling you about the past event, what has happened, what you have done, while probability is looking forward. And when you get the result of statistics also, whether it's going to be equal to what is in the population is still a matter of probability. So probability, look at this infograph. Look at a container that contains a lot of things. What probability means here is giving the information in the pail. What is in your hand? If somebody dip hand into something and close your hand, so you can predict, okay, is it white ball he took? Is it black ball or yellow or whatever? If you cannot see what is in the hand, what he's going to pick, or even if he dip his hand, what he's going to pick at random. But you have information. You have information, okay, this is a sample, this is the population of Nigeria. What proportion of them are youth and unemployed? You cannot just sit down and do that. Even though you have a mental picture of, many things in the population, but that particular question is a matter of probability. So if you now take sample as you dip your hand, so if the population of youth is so as to consider you consider so percentage, and from what has happened before, 20% and on, you'll be able to have a meta, okay, maybe it will be so percent, and it will determine how many you're going to pick. And when you pick, you see how to examine and give the result. So giving the information in the pail, what is in your hand, that is probability. That's the way it takes sample. While statistics, giving the information in your hand, what is in the pail. So after you have taken your sample now, you now examine the sample, whatever you get, you now believe that it should be close to what is in the population. Can you see? So this descriptive, that is why we talk about after you have taken your sample, you describe your data, descriptive statistics, you make projection about what is in the, you make inference about what is in the population. That is inferential statistics. I think it's making sense. Still, probability versus statistic further. You know what is in the population, what we are trying to look at is parameter. So parameter, how the world is, how the population is. You build a model around it and collect data to explain. So when you collect the data, you now use you build another model to refine the model you have built and now look at what it will be. So, and that is why today, the Bayesian method is still relevant and people are going to it now, because the Bayesian inferential approach is to combine pre and post probability. No, you do pre-test probability, post-test probability, and now combine. If you look at it, when you want to do a study, carry out a study, you want to think of, because sometimes if you just take sample, you are not mindful of the type of sample you have taken. What you are looking for may be there, you may miss it. And that is why you think of, okay, what would be the appropriate sample size. And there are some issues also. So based on past experience or somewhere else or in similar situation or in the past, what was the level of the attribute you want to measure? What was he? What did it look like? That will guide you to know the number of observation you carry out. When you are sure, you know that it's not still accurate. You still carry out the observation and still use statistics to know what is there. Now, from that statistic, you now go back to project what will be in the world, in the population. Can you see how probability and statistics relate? Now, still further, if this is the population, you take sample, unknown sample, what are the chances that all the 3 balls are red? So you want to see this is the population, you take sample. This is probability. But here, if my sample of 20 finished, product contain 5 defective pieces, how many defective pieces will be there in a whole lot of 50,000 pieces produced? That would be differential. So in this, you take sample out of 20 finished product, 5 are defective. So if you now produce, we are talking of 50,000 products, just 2 samples of 25 are defective. It gives you a clue about how many will be defective in the population of the product. Can we see how statistics and probability they work together? There cannot be statistics without probability. And our probability also, we cannot make any sense out. It will not be useful without statistics. So that's how they work together. To me, I want to agree with the person, the Fowler, that thought that the probability is bigger because it's in the world of unknown. It's the world of idea. There are many ideas. What is possible, or what those things that are possible in life, they're actually more that we don't know, and more than what we're able to achieve. It's just a matter of translating those possibilities from idea to reality. So statistics, probability try to model the idea that there are world of possibility. The probability try to theorize, to explain it. While in trying to explain it, if you take, for example, statistic is what now describe, okay, in reality, this is what we can see. And it will still give more clue about what is the world is in world of the unknown. I think it's making sense. And still further, look at this infographic, probability and statistics. If you have fear coin or bias coin, probability giving model predict data. Either is fear or bias. So if it is fear coin, you know that if you toss it, it's going to be 50. The probability of head is 50, the probability of tail is 50. If it's bias, you have to know, is it bias towards in favor of head or tail to really know if you toss it, what it will be. But it's still a matter of prediction. You can toss even the fear coin, which you think is 50-50, toss it 50 times. Almost 40-something times may be head. Yes, before you can achieve that 50-50, you may have to do thousands of times. So the probability help you build the model to predict. Now, when you take the sample through the statistics, you now build the model. So probability predict the model, the statistic will build the model, explain the world of the unknown. So look at it, giving data, predict model. So let's look at probability again. Look at in relation to population as we have been talking. You see this population, the subject what to sample, they may be human being, they may be car, they may be facility. So it's through probability you try to sample, take a subset. Descriptive statistics will now describe each of what you have there, tell you everything, summarize it, the height, the weight, color, anything, characteristic that you can use to explain the sample. Now, whatever you find there, inferential statistics will now make an inference that, look, this population, this is what is happening there. With a level of probability certainty also. And that is why when you take sample, you carry out a study, by the time you finish, they quote you, they say, Professor Susu and Eto found out that in northern Nigeria, so. Whereas he only did it in one state, maybe in Abuja, or in Kaduna, or somewhere, or maybe 2 states. Even those 2 states just select 3 local government. They make generalization. That is the inference. So that is what inferential statistics does. So the probability is create a theory around the unknown. And now took a sample, and the statistic will now explain, at least from the subset of the population, to explain, to give a clue about the unknown. So still on population parameter sampling, is a sample statistic. So look at it. You know that the population is bigger, the sample is smaller. So when you inferential statistics, how do you do after you have explained? You have taken sample. This sample statistic is descriptive statistic. Statistical inference is inferential statistic. 2 ways. You mentioned here, but there are more than 2 ways anyway. By constructing confidence interval on population parameter. Now, those are the one inferential method. You use confidence interval. Or by setting up hypothesis tests on the population parameter. You carry out a hypothesis test and end up with p-value. So we still have other methods like Bayesian method. We also have a Monte Carlo method. So, but those ones, they are not commonly used. They are not being used commonly. And you know that the commonest method are confidence interval and hypothesis testing. I mentioned people try to prefer confidence interval, especially if you want to publish in high impact journal, they prefer confidence interval, believe that the hypothesis testing has no place in medicine. So this type of statistic, just repeating what we are just saying, for descriptive statistic now, the purpose is summarizing and describing. For inferential statistic, the purpose is to analyze and do generalization. This one, summarizing, describing. But when you begin to do all those tests, statistical tests, that's what you mean by analyze here. T-test, regression, all those things. Beyond mean, mode, median, percentage, and range, which are summarizing. Summarizing, showing it in graph, showing the distribution in graph. Those are descriptive statistics, and just tabulating, giving you percentage. But when you now want to do tests so that you can make, either you do hypothesis testing or confidence interval, that is inferential statistics. Target, of course, this sample. But even though this one is done on sample, your target is you are trying to, because this one, descriptive statistics describe the sample. While the inferential statistics, even though it doesn't have access to the population, try to describe the population from the result of the descriptive statistics. So the characteristic, the summary, the characteristic you are describing is summarized as statistic for sample, summarized as parameter. For example, mean weight. For the population is a parameter, for the sample statistic. Standard deviation of weight for the population is a parameter, for the sample statistic. Sensitivity, specificity, positive predictive value, negative predictive value, rate, proportion, think of anything. For the sample, they are all statistics. For the population, they are all parameters. So it's so fundamental. We have already even shown some of our lectures also that the parameter statistics are so fundamental that even the way you denote them, like me now, mu for parameter for population, by X for statistic. Proportion, no P, population, had P for statistic. Different in mu1 minus mu2 minus it. Here is x1 minus x by x1 minus by x2. Different in proportion, P1 minus P2 at P1 minus at P2. Standard deviation rho for parameter, S for statistic. Then this one, correlation phi for parameter, R for statistic. That is Bayesian correlation. So, yeah. So we want to see what is, before we close, so that we try to look at different relationship between statistic and parameter. At least we have shown some infographics that show the relationship there. Just before we close, we want to also quickly look at what is this probability. We stop by tomorrow. We talk about distribution. We start with district probability distribution. Then later we'll talk about continuous probability distribution. Even though during our lecture on probability and normal distribution, we'll talk about that. This one is to expatiate further. There are some basic things I will not talk about here in probability, because if you go and take our lecture on probability and normal distribution, we'll talk about the nitty-gritty of probability, the approach to probability. Here is just to do what's probability, then we now, so that I can talk about the different type, because my target is the probability distribution, the different type of probability distribution. So the rules of probability, we have already talked about it, they are in the lecture. They are well explained that there's no even point repeating myself here. So probability, as we know, is a measure of chance of a given event occurring. It lies in the heart of statistical theory because it forms the basis of inferential statistics. We have already said that. For you to move any information from sample to population, the probability is involved. Because it's probability that will tell you the amount of sample, the sample size of the sample you take. Then probability that will also tell you if the result you got in your descriptive statistics, when you are making inference, is it close? How close is it to the real parameter? So it has its origin in the game of chance, such as dice and card game. So possible values of probability, as we know, is a positive number that lies between 0 and 1. Look at it, from 0 to 1. Cannot be less than 0, it cannot be more than 0. So it cannot have negative value, and it cannot be more than 1. It is, if it is 0, the event cannot occur. If it is 1, the occurrence of the event is certain. So the event cannot occur, that is uncertain. It's uncertain. But it doesn't mean that the event cannot occur, because it's prediction. You probably can say that it's 0 and it can happen. You can probability can say that it's 1. Eventually, certain it may not happen. So, you know, probability is about future. It's prediction. It's a prediction. So it's just certain or uncertain. But in real life, it can be different. So it can be expressed as decimal, such as 0.2, 0.5, 0.8. It may be given as fraction also. I say 2 over 10 instead of say 0.2. I say 1 over 2 instead of say 0.5. Or 80 over 100. So in this case, if it's 80 over 100, that becomes a percentage. It's 80%. So 80% is the same thing as 0.8. 50% is the same thing as 0.5. 20% is the same thing as 0.2. The probability of a complementary event not occurring means that a complementary event is 1 minus probability of the event occurring. That's what if I say that, oh, the probability that it will rain tomorrow is 0.6. That is the probability. The probability of complementary event is 0.4, because the complementary event is that it will not rain tomorrow. That's the complementary for it will rain. So that is, they are added up to 1. So now that one leads us to probability distribution. What does it mean? Probability distribution. This is where I want people to have understanding, because people are confused when it comes to distribution. What is the meaning of distribution? In our lecture on distribution, we said that distribution on its own is pattern of occurrence of value of a variable in a data set. We talk about frequency distribution, relative frequency distribution, cumulative cumulative frequency distribution, cumulative relative frequency distribution. Those 4 types, those are the 4 types of distribution. But still beyond pattern of occurrence of variable in a data set, distribution also, we have special type of distribution that talk about sampling distribution. So when we talk about the probability distribution, both distribution of raw data and sampling distribution, all of them, they are all probability distribution. The funnest thing, anything distribution, they are probability distribution. So that's why when somebody says that statistics is a subset of probability, is right. So everything you are doing in statistics is actually explaining probability theory. The probability there is what is explaining, try to predict the unknown. And it's so vast. There are a lot of things to be known in universe. So if you say that what's the scope of probability, as the universe is big, it's the same thing. There are many things you don't know. You can only just speculate, predict, and that's the domain of probability. But if the one you're able to lay your hand on, statistics will now help you to explain it. So what you are saying, is it true or not? So statistics is more practical, but it's still explaining it based on the rule laid down by probability. That's just it. So distribution that shows the probability of all possible value of random variable. No, that is, if we say, okay, as we are in this class now, what is the probability distribution of the sex? So the probability distribution of sex here is how many of us, we have only 2 possible values of sex. You have to first of all. So all possible values of a random variable. If you choose sex as a random variable, we have 2 possible values. So if we now say, okay, how many are male, how many are female? You put male over the total and know the fraction or the percentage, move female over the total and know the. If you even know one, you know the other one, because if female are 60%, automatically the male will be 40%. So you will see that it cannot be more than 1, 0.6, 0.4. When you total everything to be 1. So probability distribution is the probability of all the possible values. So this one I just explained is the simplest one because it follows the binomial in the sense that there are only 2 possible values. Of course, if something is only 1 value, it's not a variable, it's not a random variable in the sense that if everybody is a female in a class, or maybe you are doing study in O&G department, all their clients are female. So the sex is not a variable, it's not a random variable. So the simplest random variable we have, 2 values, possible values. Yes. And that is male, female, yes or no, head or tail, anything pass or fail, anything that, and that is why clinicians like this binomial. And that's why they like logistics, anything. You just want to separate the people they need to treat and from people they don't need to treat. So you just look for something as a cutoff to divide into 2. And that's why in epidemiology also, epidemiology put everything on 2 by 2 table. The outcome you are measuring, you put it 2 possible value. The exposure will make it 2 possible value. It still give you 2 by 2 contingency table, 4 sets. That's the simplest, and that's the simplest contingency table. Now, probability distribution, probabilities of all possible value. Like if it was, it's easy to use the classical approach. That's what I'm using. The issue of coin, there's a classical approach. And the issue of dice, classical approach. Classical means that there's this established setting for each of them. For coin, now we know there are 2 faces of a coin. So even though some people come with some philosophical say that the 3rd face of the coin. But there are 2 faces of the coin. If you bring a die, there are 6 faces of a die. So these are classical approach because it's already established. You can really say, okay, what is the probability if I throw the die? You give me 1. And 1 is written on 1 face out of the 6. So these are classical approach. So the possible value of throwing one die is one. There are 6 different. 1, 2, 3, 4, 5, 6. So the probability of each of them, the list of all those 6 and their probability distribution for that coin for that die. That's the issue of die and coin. They are classical approach. Example of frequency approach. Relative frequency approach is the one we have just said. Okay, out of the exam they did, what proportion of pass or fail? No, there is no established setting that a certain proportion will pass or fail. So you just have to calculate it from the exam, the most recent one. Or if you want to, if the proportion of female, there's no established setting that says that it has to be 50-50. Unless you do the census to really know what is the real proportion based on the latest. So that one, it has to be relative frequency. That is, you have to have collected a sample. And what is the relative frequency? That's what they call it, relative frequency. So whichever way, people don't know that when you tabulate your result, you put the percentage, you don't know that it's probability distribution that you have shown. You have shown. Because you show all the values and the probability. You show in the form of percentage. 50% means 0.5. And you make sure that none of them is more than 100. Because if it's more than 100, there's a problem. You cannot have total and you are having more than 100. 100% is the, so 100% means 1. So all the probability for each variable will be added for the outcome, for all the outcome of each variable, you added 100. Like ethnicity, you do Hausa, Igbo, Yoruba, others. The percentage must add up to 100. So what you don't know that is probability distribution of the ethnicity you just put there now. If it's geopolitical, it's the same thing. So now, random variable. Okay, what does that random variable mean? It means quantity that can take one of a set of mutually exclusive value with a given probability. That's what this one is a little bit sometimes you know when you are trying to understand something, so people see bring another term. But just know that any variable, I said it the other time, any variable that the outcomes as a result of random process, that's another way of saying it. But the simplest one is that any characteristic that varies from one person to the other, you may not have the same, you will not have the same value for everybody. That's variable. So forget about this, the Greek grammar, random variable, random process. Now, a probability distribution is a theoretical distribution that is expressed in tabular form, graphically or mathematically. That when we say distribution, is either you say something, either you got it from classical approach or relative frequency. It's theoretical in the sense that probability usually is just giving you, is predicting what it will be. When I usually give an example, when I facilitate this session on probability, I say that if your friend that is European, that has not come to Africa, is coming to visit you, and he has never come to Africa, and what's the probability that the person will develop malaria if you don't take prophylaxis for the person? So many people will say many things, but the issue is that the most important one will be the most valid advice will be based on study that have been done before recently. How many Europeans that came to Africa or Nigeria without prophylaxis and now develop, what proportion develop malaria? So that recent study is what you do. So you see, you have gotten it from a study. That is relative frequency approach. If it is classical approach, you cannot use the classical approach for that situation. The issue of throwing die, all those, because they are established setting, throwing coin or die. Those are classical approach. Whether through classical approach or relative frequency, you are still predicting what you are. When you tell me that 40% of the Europeans are developing malaria, so you are telling me that it's something that happened in the past. You are predicting that maybe it may still happen. You are not, the probability that you develop malaria will be 40% because based on the past. Can you see? You are predicting the future based on what you observe in the past. That is it. So that is why it's a theoretical distribution. And that's why even when you say tossing a coin, say 50-50. So believing that if I toss you 100 times, 50 will be head, 60 will be head. Toss you 100 times, you may get even 90 something head or tail. So it's predictive. It's just predicting. It's a theoretical distribution that is expressed in a tabular form. Tabular put in a table, you put each value in a table and put the probability beside, or you show in a graph. And that one is more appropriate with continual probability distribution, or you do in mathematics, mathematical equation. So just like a model. So each probability distribution is defined by certain parameter characterizing that distribution. Two important characteristics of probability distribution. The probability of a particular outcome must always be between 0 and 1 inclusive. That is, there's no probability that can be greater than 1. That is, any probability value you want to give for an outcome, it will be anything from 0 to 1. It can be anything between 0 and 1. Inclusive, it can be 0, it can be 1. The sum of the probability of all the mutually exclusive outcome is 1. That is, for a particular variable, if you look at like for ethnicity now, you say, Hausa, Igbo, Yoruba, all that. If you had all the probability, what proportion in your study, what proportion is Hausa, Fulani, what proportion is Igbo, what proportion is Yoruba, what proportion is other. When you now put it over upon total, it should not be more than 100% 1. It will still add up to 1. That's like two major rules. Then the type of probability, I think we'll stop here. By next tomorrow, we'll start discussing the different type of probability distribution. Where we talk about discrete and continuous. Where we look at district. We're going to look at district. Okay, let me just wait that with this slide, this one slide. So there are, although the space of possible probability distribution function is infinite. That is, if we are talking about type of probability distribution, you can, if you go and check it's infinite. In fact, many people will describe new one. So you cannot say there are 3 types. No, you may have 3 categories or 2 categories, but there are different types of probability distribution. Infinity, you can, people will continue describing different things. There are a handful of common distributions that can be used to appropriately model a wide range of problems. It's just for you to know some common one that you can use in many situations. So because there are some of them also, you can use more than one in a particular situation to model a particular situation. So because of that, we have infinite number of probability, different types that people will describe. But the commonest one is what we want to be looking at. But whichever way, whether even if there are million or more than million, there are 2 categories of probability distribution: discrete and continuous probability. So any probability distribution will be either under discrete or continuous. In discrete, the probability distribution in which we can derive probability corresponding to every possible value of random variable. The example I'll be giving, they are discrete, like sex, like the issue of die or whatever, or issue of ethnicity, or issue of whether somebody developed malaria or not, because it's never a matter of yes or no, it's binomial. That is discrete, because you have possible number of, manageable number of outcome, category of outcome, like sex that we have 2 possible. Even if you say that we have hermaphrodite, okay, let's say male, female hermaphrodite, and are manageable, you know them. Like ethnicity, even if you say we have 300 ethnicity, we know them. Even though for convenience sake, we collapse some. When we mark the major out, we collapse some. But there are some probability distribution that you cannot know all the possible value. So if you cannot know all the possible value, you cannot know all the possible probability. For the discrete, you can know all the possible outcome. So when you know all the possible outcome, you can know their probability and list it. And that's what you usually do your result. But for continuous variable, like blood sugar, how many possible blood sugar you have? infinity. You can have blood sugar 60, 60.0, 60.1, 60.002, 60.009, 60.0019, infinite. Even between 60 and 1, they're infinite because they're decimal. So for such variable that it's not possible for you to say this is the number category of blood sugar we have, okay. What are the blood sugar you have? Let's divide the over. No. So it's not possible for you to know the probability of all the blood sugar. So you cannot know it. You can only know, so that because of that, you cannot know what is the probability that the blood sugar is 64. It's not possible. What you can know the probability that is between 64 and 65 or 66. No, you use 64 and 100. So you can know the probability of a range of value. Or you can say probability that is above 60, below 60, between 16 and this, between this and this. That's all you can know. The probability of it. For continuous variable, you can only know the probability of a range of value. You cannot know the probability of a given value because there is no denominator. You cannot know how many are possible. And the reason you can know a range of value is that you can now use graph to show it. We call probability density function. So we talk about that later. This is just a clue. So you can see now, maybe by next tomorrow, we'll talk about discrete probability distribution. I will still talk about this so that you're able to understand. I don't know if there's any question. We'll stop here. Yeah, so I can see some chat. Thank you. Idea example of classical probability in medicine. Your classical have any relevance in medicine? Well, that's a very big question. Yeah, you still have, because sometimes we gamble in medicine, we ballot. So if we ballot, well, unless in a situation where you want to choose between two, you have two for no reason. Yes, it has place now. When you are randomizing to two groups. When you are doing so, you want to do randomized control trial. You are randomizing. You already know that there are two possible, and for where you have already put yes, no, A or A, B. So if you are going to choose for random for that person, is either A or B. For that person, is 50-50. So that's the only situation. So there is no, because if you look at all those classical something, the probability and statistics started from a game of chance, or this gambling. So that is why something like Tosi coin, die, and some other thing that has some setting, already established setting, you used to study probability. So I think those are the situations. So naturally, I don't think there's anything that you say, okay, it's either this or this. Well, there are some things like that. If somebody, if somebody has, if you're an ophthalmologist, somebody has glaucoma, have a patient glaucoma, will see you. If it's one, it's either a right or left. So I think those are the usefulness. It's useful theoretically. So any other question? Yes. So you said in binomial distribution, there are two variables. What about when there are three or more variables? I did say there are two variables. When you are talking of one variable, there are two possible outcomes. That's what I mean. Maybe that's what it's not variable, the outcome of that variable. Like sex is a variable, so there are two possible outcomes, male or female. Tossing a coin, one is a variable, the coin is a variable, tossing a coin is a variable. You can either be head or tail. If you ask a question, yes or no, is a variable, is a binomial, is followed by binomial, either yes or no. Any question that is either yes or no. Hypertensive, not hypertensive. Is he obey, not obey? So these are, I don't know if it's clear now. Any other question? Okay, that's great. So if you have, what you can be asking that if you have more than 3 outcomes, if they are discrete, we call it multinomial. Binomial means 2 possible outcomes. Once they are more than 2, it's binomial. We just call them nominal variable because there are some more than 3. Why they don't usually use, well, more than 3, it may be ordinal. That is, it's gradient like economic status. There are 3 categories, but they see that they are not the same level. You can see greater than or less than, you can see gradient, like upper, middle, lower. That will be ordinal variable. Okay? It's a form of categorical variable. Okay? Okay, any other one? No, if there's no any other question, you can ask your question. You want to ask, you want to talk, you can talk. Okay, if there's no, okay. Okay, if there's no other questions, let me just off the impulse.